Hey everyone, welcome back. This week, we're diving into the top AI research papers. We'll explore advancements in areas like AI video generation, 3D material creation, and human motion prediction. Get ready for a step-by-step breakdown of each paper, making these complex concepts easy to understand. Let's explore the exciting world of AI. Paper number 1: Building Effective Agents, a practical guide for AI agents. Today, we're diving into a really interesting paper from Anthropic titled Building Effective Agents. What makes this paper unique is its focus on practicality and simplicity in building AI agents. Instead of pushing complex frameworks, the authors argue that the most successful implementations use simple, composable patterns. They emphasize that it is about building the right system for your needs, and not necessarily the most sophisticated. The paper starts by distinguishing between workflows and agents within what they call agentic systems. Workflows use predefined code paths to orchestrate LLMs and tools, while agents dynamically direct their own processes. The authors recommend starting with the simplest solution possible, using LLM APIs directly, and understanding the code if frameworks are used. The basic building block of these systems is the augmented LLM, which includes retrieval, tools, and memory. The paper then explores several workflow patterns, such as prompt chaining, which decomposes tasks into steps, routing, which directs inputs to specialized tasks, and parallelization, where LLMs work simultaneously. More advanced workflows like orchestrator workers and evaluator optimizer are also explained. Finally, the paper discusses autonomous agents, which operate independently. The paper highlights the importance of simplicity, transparency, and thorough tool documentation, giving examples of agents in customer support and coding. The core message of the paper is that success in building AI agents lies in understanding fundamental building blocks and adding complexity incrementally, rather than starting with overly complex systems. Paper number 2: DeepSeek V3, a highly efficient mixture of experts language model. We're diving into the DeepSeek V3 technical report. This paper introduces a truly unique and powerful mixture of experts language model that is also incredibly efficient. DeepSeek V3 has a staggering 671 billion total parameters, yet it only activates 37 billion parameters per token. This efficiency is achieved through innovative techniques like multi-head latent attention, MLA, and the DeepSeek MOE architecture. These architectural choices allow for a large model that is still practical to use. The paper also pioneers an auxiliary loss-free load balancing strategy that prevents performance degradation, and introduces a multi-token prediction (MTP) objective to further enhance performance. The model is pre-trained on a massive 14.8 trillion tokens. DeepSeek V3 uses an FP8 mixed precision training framework, which significantly improves training efficiency and reduces costs. The pre-training stage required just 2.664 mH800 GPU hours. Post-training includes a unique method of knowledge distillation from DeepSeek R1, designed to enhance the model's reasoning capabilities. The training process is also notable for its stability, with no reported loss spikes or rollbacks. Evaluations show that DeepSeek V3 achieves state-of-the-art performance across a variety of benchmarks. It outperforms other open-source models and is competitive with leading closed-source models. It also supports a 128K context window. The model is available on Hugging Face, and the DeepSeek V3 series of models supports commercial use. Paper number 3: ModernBERT, a Pareto improvement over BERT for encoder-based tasks. We're diving into a game-changing paper titled, Finally, a Replacement for BERT, Introducing ModernBERT. What makes this paper unique is that it introduces ModernBERT, a new family of encoder-only models that are a Pareto improvement over BERT and its successors. This means ModernBERT is better in almost every way: faster, more accurate, and with a longer context length. ModernBERT achieves this by incorporating recent advances from large language models into a BERT-style architecture, including updates to both the model architecture and the training process. It is designed as a slot-in replacement for any BERT-like model and is available in both base, 139M parameters, and large, 395M parameters, sizes. ModernBERT's improvements come from three main areas: a modernized transformer architecture, particular attention to efficiency, and modern data scales and sources. The architecture incorporates rotary positional embeddings, rope, GPU layers, and removes unnecessary bias terms. It uses alternating attention, alternating between global and local attention, which makes it significantly faster with long inputs. ModernBERT also uses unpadding and sequence packing to reduce computational waste. For training, the model is trained on 2 trillion tokens, including code, scientific articles, and web documents, unlike older models that use more limited corpora. ModernBERT has a context length of 8,192 tokens, compared to 512 for most encoders. This makes it ideal for applications like retrieval augmented generation, RAG, code search, and other tasks where long context is needed. It is also faster than other comparable models, sometimes by as much as 2 to 4 times. The paper also stresses ModernBERT's practicality and efficiency, ensuring that it works well on affordable consumer GPUs. This makes ModernBERT an attractive option for a wide range of applications. Paper number 4, Nymeria, a multimodal dataset for egocentric human motion understanding. We're discussing the groundbreaking paper, Introducing Nymeria, a dataset for improving human motion prediction for AR and VR devices. What makes this dataset truly unique is its focus on capturing egocentric human motion in real-world settings, using multiple multimodal sensors like Project Aria glasses and Mini Aria wristbands. Unlike previous datasets often gathered in controlled labs, Nymeria offers 300 hours of multimodal egocentric daily motion collected from diverse participants in varied locations. The dataset includes 20 predefined, unscripted scenarios like cooking, sports, and socializing, capturing how people perform activities differently. This in-the-wild approach helps researchers build technology to assist daily human activities. Another key aspect is its multimodal approach, combining signals from various sensors to mimic data from future wearables. This enables researchers to improve body movement prediction for devices like AI glasses and smartwatches. The dataset also includes human-annotated descriptions of the motion, bridging the gap between movement and natural language. This allows researchers to explore advanced techniques with LLMs and develop user-friendly solutions. The dataset's multi-level narrations help model human motion, actions, and activities at varying levels of detail. The Nymeria dataset addresses the challenge of predicting body position from egocentric sensors, which is difficult due to human movement complexity and current device limitations. By making this dataset public, researchers aim to accelerate egocentric human motion understanding and develop personalized AI assistants. The dataset facilitates the creation of more accurate models for full body motion tracking, leading to better user experiences in AR/VR and other wearable tech. Paper number 5, ASAL, Revolutionizing Artificial Life Research with Foundation Models. We're exploring the groundbreaking paper, Automating the Search for Artificial Life with Foundation Models. What makes this paper stand out is its pioneering use of Vision Language Foundation Models, FMs, to automate the search for interesting artificial life, A-life, simulations. Traditionally, A-life research has been limited by manual design and trial and error, but this paper introduces a new method called Automated Search for Artificial Life, ASAL. ASAL allows researchers to explore vast spaces of possible simulations, identifying those that exhibit complex behaviors or match specific criteria. The ASAL framework utilizes FMs to evaluate simulation videos and incorporates 3 distinct search mechanisms: finding simulations based on a text prompt, discovering simulations with open-ended novelty, and illuminating a diverse set of simulations. This approach is effective across various A-life substrates, including voids, particle life, game of life, linea, and neural cellular automata. ASAL has discovered previously unseen life forms and expanded the scope of emergent structures in A-life, such as exotic flocking patterns in voids and novel self-organizing cells in linea. Furthermore, the use of FMs enables the quantification of previously qualitative phenomena in a way that aligns with human perception. This FM-based approach is substrate and FM agnostic. This means that the method can be used with other A-life simulation substrates and different types of FMs. This innovative method speeds up discovery, shifts the focus from manual design to defining desired outcomes, and makes A-life research more scalable and efficient. It promises to push the boundaries of what's possible in A-life research beyond human ingenuity alone. Paper number 6, GenHMR, a probabilistic approach to human mesh recovery. We're diving into the fascinating world of 3D human pose estimation with the innovative paper, GenHMR, Generative Human Mesh Recovery. What makes this paper unique is its approach to monocular human mesh recovery as a generative task, explicitly addressing the uncertainties inherent in mapping from 2D images to 3D models. Unlike deterministic methods that output a single prediction, GenHMR uses a probabilistic approach to generate multiple plausible 3D reconstructions. This is crucial because recovering 3D human poses from a single 2D image is inherently ambiguous. GenHMR uses a pose tokenizer to convert 3D human poses into a sequence of discrete tokens in a latent space. Then an image conditional mask transformer is used to learn the probabilistic distributions of these tokens based on the input image. The model uses uncertainty-guided sampling (UGS) during inference to decode high-confidence pose tokens iteratively. This process is followed by a 2D pose-guided refinement technique to fine-tune the decoded pose tokens. This ensures that the projected 3D body mesh aligns with 2D pose clues and further reduces uncertainty. The refinement process iteratively corrects errors, with significant improvements in the first 10 iterations. GenHMR outperforms state-of-the-art methods, especially in challenging scenarios with unusual poses or ambiguous situations. By explicitly modeling and mitigating uncertainties, GenHMR achieves more accurate and robust 3D pose reconstructions. The method has shown significant improvements in accuracy through the refinement stage. Paper number 7, SCENIC, Instruction-Guided Control in 3D Scenes. We're diving into another exciting paper called SCENIC, Scene-Aware Semantic Navigation with Instruction-Guided Control. What makes this paper stand out is its innovative approach to text-conditioned scene interaction. Unlike previous models, SCENIC can navigate complex 3D scenes with varying terrains, while also supporting user-specified semantic control using natural language. This means you can tell it to perform specific actions, like hopping over the stool and sit, and it will understand the scene and execute the motion accordingly. SCENIC achieves this through a hierarchical reasoning of the scene. It uses a goal-centric approach to understand high-level objectives and altitude differences, and a human-centric distance field to manage granular details. The model also uses frame-wise alignment between motion and text to allow for smooth transitions between motion styles. To train the model, the researchers used paired motion scene text data, fitting real human motion segments onto synthetic terrain patches. This method effectively increases the amount of training data available. The model was tested on 4 real-world scene datasets: Replica, Matterport, HPS, and Laser Human. The results show that SCENIC can avoid undesirable penetrations and floating artifacts, demonstrating its ability to generalize to different scenes and text prompts. The model can seamlessly transition between diverse motion styles based on the user-specified text. This research opens up new possibilities for creating more intuitive and realistic virtual agents and environments. Paper number 8, CausVid, Real-Time Video Generation. We're exploring the cutting edge of video generation with an exciting paper titled From Slow Bidirectional to Fast Causal Video Generators. What makes this paper truly unique is its ability to generate high-quality videos in real time, or as they put it, instant video generation. Current video diffusion models, while producing impressive results, are often slow due to their bidirectional attention dependencies, requiring the entire sequence to generate a single frame. This paper addresses that limitation by creating a causal transformer that generates frames on the fly. The researchers achieved this speedup by distilling a slow, multi-step bidirectional video diffusion model into a fast, four-step causal generator. The training process involves 2 key stages. First, they initialize the causal student model by pre-training it on a small set of ODE solution pairs from the bidirectional teacher model, which helps stabilize training. Second, they use asymmetric distillation, training the causal student model with a bidirectional teacher model using a distribution matching loss. This approach effectively mitigates error accumulation during the autoregressive generation, enabling the synthesis of long-duration videos despite training on short clips. This new model, called CausVid, achieves state-of-the-art text-to-video generation quality, outperforming other methods in various metrics and enabling fast streaming inference at 9.4 FPS on a single GPU. It supports interactive use cases like text-to-video, image-to-video, and dynamic prompting in a zero-shot manner. CausVid also enables the generation of infinitely long videos through sliding window inference. Paper number 9, MCMat, Multi-View Consistent PBR Material Generation. We're diving into a fascinating paper called MCMat, Multi-View Consistent and Physically Accurate PBR Material Generation. What makes this paper unique is its 2-stage approach to creating realistic PBR, physically based rendering, materials for 3D objects. Unlike existing 2D methods that struggle with multi-view consistency or 3D methods that have generalization issues, MCMat tackles these challenges head-on. In the first stage, the model, called Multi-View Generation DIT, MGDT, uses a diffusion transformer, DIT, model to generate PBR materials. It utilizes surface normal information from the 3D model, along with reference images and text descriptions, as conditions. The model uses a global attention mechanism to ensure consistency across multiple views. It also uses a PBR-based diffusion loss to make sure the generated materials adhere to real physical principles. In the second stage, the Material Refinement DIT, MRDT, model refines the material in UV space by performing in-painting in void regions and enhancing details. This stage takes the material map from the generation stage as an additional condition to reduce learning difficulty and improve generalization. The result of this two-stage approach is the generation of high-quality 2K resolution textures with precise material information. The method is particularly useful for texturing 3D objects and has significant advantages for graphics relighting applications. Examples of generated textured meshes include sunglasses, a tiki mask, a Colt M1911, and even a Power Ranger. Paper number 10, INFP, Audio-Driven Interactive Head Generation. We're diving into another fascinating paper called INFP, Audio-Driven Interactive Head Generation in Dyadic Conversations. What makes this paper truly unique is its ability to generate dynamic and natural head movements for virtual agents in dyadic, or two-person, conversations. Unlike previous methods that require manual role assignments between speaker and listener, INFP can automatically adapt to different conversational states, leading to a much smoother interaction. The INFP framework consists of two main stages. First, in the motion-based head imitation stage, the model learns to translate facial expressions from real-life conversation videos into a low-dimensional motion space. These codes are then used to animate a static portrait image. Second, in the audio-guided motion generation stage, the model learns the mapping from the input audio to the motion codes. This is achieved through a denoising process, allowing the model to drive the head generation based on audio input from both speakers. This approach allows INFP to generate realistic facial expressions, rhythmic head movements, and lip-sync accuracy based on the audio. The model is also lightweight and fast, achieving over 40 frames per second on an NVIDIA Tesla A10, making it suitable for real-time communication scenarios. This is especially important for practical applications such as video conferencing or human-agent interaction. INFP can also support diverse outputs, such as non-human realistic faces, side-view faces, singing, and different languages. The model can also generate diverse head motions for listening and talking scenarios. That's it for this week's top AI papers. We covered a lot, from CausVid's video generation to INFP's head movements and MCMat's 3D textures. We also discussed SCENIC, Nymeria, GenHMR, ASAL, ModernBERT, DeepSeek v3, and building AI agents. Let us know your favorite in the comments. Don't forget to like, subscribe, and hit the bell for more AI content. See you next time.